Go ahead.
Okay. Okay. All right. So I wanted to present this talk, and it's a sort of this is not about the frustration that you may experience as a researcher or something. We've had sort of events like that, but this is not this. This is about frustrated systems, so spin glasses, and I will explain what this is. And there's a lot of talks like this year at conferences by people who are far more eminent than me in this area. And obviously of those, while I have been on this planet for those 50 years, consciously, I mean, you only start kind of thinking at the end of your PhD, right? So say 25 years in my case, okay? Say, or 20, 25. So these two papers sort of define that field, and they're both from 1975. And the one by Edwards and Anderson, and the one by Sherrington and Kirkpatrick. And I would like at this point to acknowledge David Sherrington, who was my PhD advisor. So I feel sort of grateful to be able to present this. So these appeared sort of within a few months from each other. So these are the four gentlemen, Sam Edwards and Phil Anderson, who are no longer with us, and David and Scott, who are active. So now what is this about? So I don't know, this is sort of probably not taught in a regular undergrad course or graduate course, maybe, I don't know. So, but you all know what a ferromagnet is, right? So a spin system where spins want to align with each other. So this is an example of a configuration like this. And then there's antiferromagnets where each spin wants to kind of point in the opposite direction than the neighboring spins. And then there's something like you would call it a paramagnet. So the spins sort of point in random directions. So here, these are not up-down spins, right? So they are meant to be sort of, they point in arbitrary directions. So this could be a paramagnet, but this could also be a snapshot of a spin glass. And what's the difference? So the difference is in a paramagnet, or in the paramagnetic phase of a model like this, these spins fluctuate around, right? So if you look at any one of them, they sort of just go up, down, sort of randomly. Whereas in a spin glass, they are sort of frozen in time. So if you look at any one time, you see something like this. But if you look again, it will not be a completely different configuration. It will be sort of similar. It will be disordered but frozen. So these are frozen and ordered, and this is frozen but disordered in a way. So that's sort of the idea. And these kind of ideas were around, I don't know, since the early 70s, I believe. And then people had sort of investigated this, and there were some ideas, but it wasn't clear whether there was a real phase transition or not. And then there's this paper by Canela and Maidos, and where did this sort of the first evidence of a real phase transition, I think. And this Maidos is also, so I was at the conference in July, and he was there. So these are on systems where you have a host, which is some noble metal, for example, and then you have some impurities that are magnetic. So for example, iron. And this is from their paper. And this is the susceptibility, so it's sort of the response to a magnetic field as a function of temperature. And then you see this peak, this cusp, which sort of indicates that something is happening there. So there's some sort of phase transition there. And people looked at this in a lot of detail. Then they looked at things like the magnetization of this sample, of a sample, of samples as a function of temperature. And then you have here, at high temperatures, you have sort of one branch here, which looks like a paramagnet. So here, and then below a certain temperature, Tg, so glass temperature, what you see then depends on how you do it. So there is a branch here that is called field cooled. So you cool the thing in the magnetic field, and then you see this. And here you have no magnetic field, you cool, and then you switch on the magnetic field. And then you see sort of this. So you cool it up to here, for example, and then you switch on the magnetic field. Or you cool it up to here, and then you switch on the magnetic field. You see this. This one is more or less reversible. This one is sort of different, right? So it's a different branch. And there's a difference between them. And and then you can look at the susceptibilities in a bit more detail. So there's an in-phase component and an out-of-phase component. And so the in-phase component is this. So that's looks essentially like this. But then there's the out-of-phase component, which is 0 in the paramagnetic phase. So if you have a paramagnet and you have an oscillating field, it sort of follows. There's nothing out of phase. It just follows. But below this temperature, there's also a kind of out-of-phase response. So some sort of delay in the system. So there's some kind of memory effects in there. And then people looked at the correlation time of spin. So how the persistence time of a spin, how long does it sort of take to flip, if you like. And this shoots up. So this is T over the critical temperature, T over T glass. And this goes here from kind of 10 to the minus 10 to 10 to the minus 5. So 5 orders of magnitude as you go from sort of, I don't know, 1.5 times the glass temperature to, I don't know, 0.5 times the glass temperature. So there's a relatively sudden dramatic increase here. And then there is something that is called the Edwards-Anderson parameter that we'll talk about in a minute. So this is sort of, I look at a particular spin and I take the thermal average. That's the square bracket, and I square this. So if the spin was going up and down all the time, this object would be 0, right? The square bracket would be 0. And then I average this over spins, if you like. And if this thing is non-zero, then it means that there's some kind of freezing of the spins. And this is indeed what you see. This is from a later paper. There's data here from some material and then from simulations. And there is, again, some kind of temperature at which this thing becomes non-zero. And then this a thing that I find is very interesting. There's a phenomenon that is called aging. And this is not the aging that people talk about here sometimes in the Voter model or something. So imagine the following. You start at high temperature somewhere, and then you quench. You go below the glass temperature or the freezing temperature, and then you remain at that temperature. And then you have a magnetic field that you leave on, and after some waiting time, after you've done that quench, after some waiting time, you switch the field off, and then it remains off. And then you measure the magnetization in a sample, and then you see this kind of thing. So it decays then, right? So this is from this point on, sort of, right? So you have the field on, then you switch it off, and then the magnetization decays. But what is plotted here is different curves for different waiting times here. So the field has been on longer here for this curve than for that curve. And what is plotted here is in fact not time, it is T divided by the waiting time. And all these curves more or less collapse onto one curve, more or less. So this means that the relaxation, the longer you waited here, the more slowly this thing decays afterwards. So the sample ages. The longer you wait, the higher the age, the longer it takes for this thing to sort of lose its magnetization, if you like. So this is what's called aging in these materials. Okay, so the properties of the spin glass phase are more or less frozen in magnetic moments below some freezing temperature. There's no real long-range order, and there's some kind of aging or magnetic relaxation on macroscopic timescales. You can find this in a lot more detail, for example, in this review by Binder and Young. And there's also has aged a bit. But anyway, it's a useful source. So now how does this work, or what creates this effect? So there are these impurities, and they produce some kind of magnetic polarization in the host, in the conduction electrons of the host. And this polarization, the nature of this or the sign of this depends on distance. It can be negative or positive depending on distance. And then the other impurities then feel this. So this originally, I think if you look at a single impurity, then this goes on the Kondo effect or something like this. And then this now is about how do different impurities interact with one another. And what one finds is that the interaction between different impurities, the nature of these interactions depends on distance in this oscillatory manner. And this goes under the name RKKY interaction. And these are the 4 names. So you can have positive or negative interaction between these impurities depending on distance. But these impurities are sort of in the sample at random positions. So they have random distances from one another. And this is a cartoon, and this is sort of experimental data where you can actually see this kind of oscillatory dependence of this interaction parameter on distance. So interaction depends on distance and can be positive or negative depending on distance. And these impurities are located at random positions. So this means that the interactions between the impurities are random, and some are positive and some are negative. So it's like this. So this is from the Nobel Prize page, 2021. So you have these impurities, and they have some kind of, they are randomly scattered in this sample, and they interact. And whether the interaction between any of those is positive or negative, any two of those, depends on their distance. So the two key components are positive and negative interactions and randomness. So, and that together leads to what's called frustration. And that term, I think, was first used by Gérard Toulouse in this paper from 1977. So, and this is frustrated systems. And so if you have so I'm now going to show a series of these kind of cartoons. So this is meant to be, these are 9 sites for spins. And whenever you see a green link here, this is a ferromagnetic interaction. So this is a ferromagnet, and of course this is very easy, right? All the spins, the ground state is all spins up or all spins down. So everybody knows this. Then you can have they have a situation like this where you have some positive and some negative. So red bonds are antiferromagnetic bonds. So these two guys want to be anti-aligned. But this is not in Toulouse. Toulouse describes this as this is not serious disorder, because of course there's an easy configuration that minimizes energy. I just have to flip the central spin, right? So this. So then all the bonds are happy. Everybody's happy, right? All interactions are satisfied. But I can have a more complicated situation where I have sort of randomly made these green or red, and then it could look like this. And then it's not so easy what the ground state is, or what configuration minimizes energy. So look only at these 4, for example. So if this one is up, then if you want to follow this bond, this one has to be up. Then this one is green. This one has to be up. But what do you do here, right? You have to either put it up or down. If you put it up, you make these two happy, but these two are unhappy, or the other way around. So you can't satisfy all interactions here. So if you have a plaquette like this, you have sort of the options. You always break at least one bond. You can't make all 4 bonds happy. So no matter what you do, you can't make everybody happy. But then there's in this case 4 configurations that are sort of all equal in terms of energy. So there's a multiplicity of compromises, if you like. So, and then so how does one model this? And these are the 2 models, Edwards-Anderson and Sherrington-Kirkpatrick. And so Edwards and Anderson assumed, let's say, they have vector spins, so say XY spins, and on a lattice, and you interact with your nearest neighbors. So then you have a Hamiltonian like this, and Jij is the coupling between spin I and spin J. And the Jijs in both of these models are random couplings that are drawn from some distribution with a given mean and a given variance. But you draw them at the beginning, and then you look at this. So they don't change as you look at the system. And the Sherrington-Kirkpatrick model is similar, but so they simplified it in the sense that these are binary spins, plus or minus, so Ising spins, and it's all-to-all interaction. So everybody interacts with everybody. So this is sort of going from vector spins to binary spins, and then this is sort of the mean field version of this in a mean field geometry. And then now I'm taking this from David's lecture notes. There's a very simple argument. Okay, you have the SK Hamiltonian. And then you say, well, if you do naive mean field theory, as you would do for the Ising model, you would write down something like this, right? And then you say, well, when does this have a non-zero solution? And then you say, well, okay, when does it have a small solution? So you linearize this thing. So then you get this, right? You get this equal to the argument for when this argument is, you ask, when does this thing have a non-zero solution? What is the onset of a non-zero magnetization? And you get this. And then if you take now the average over the disorder, this is the bar, unless there's a kind of systematic ferromagnetic or antiferromagnetic component here, you will find if this thing is 0, so if on average these couplings are 0, you will never have a non-zero solution here, right? Because then the right-hand side is immediately zero. So this is also a completely naive way of doing mean field theory here, but okay, so it gives you some indication. And then you can say, well, okay, let me look at the square of this object. So let me linearize this and then square. Then I get something like this, again, ignoring correlations and everything. I get something like this. And then I find all of a sudden this has a non-zero, this can have a non-zero solution here for this quantity. So if I call this thing Q, and I have here Q squared and this is also Q, I would have this. And then this thing can become non-zero at this temperature. And this is exactly this Edwards-Anderson parameter that I mentioned earlier. So then it's possible for these spins sort of to be frozen in. But again, this is completely naive. And now, can we do a better theory for this? And okay, so this is the Hamiltonian, the SK Hamiltonian. And then the free energy is this. And where I've indicated J here, that this thing depends on the particular realization of these couplings. And Z is the partition function like this. And then you have to average this over the disorder, right? You want to say what happens in a typical sample. So if I average over the assignments of these Jijs. So you want to average this object over the distribution of J. So that's this overbar. So then there's a question, how do you do that? You have to average the logarithm. So this is, you can do sort of, you can simplify it and say, well, okay, let me not average the log, but just let me average the thing inside the log and then take the log. But that doesn't produce the right thing. So you have to do it that way. And then, well, what do you do? Now, this is not so easy, right? So how do you average this object? And this is what Edwards, I think, came up, well, I don't know, both of them, I don't know who, came up with the replica trick. So the log of Z can be written in this way. So you want to average this thing. Okay, well, then average this thing and then take the limit in little n to 0 after you've done that. And now what is Z to the n? This is the partition function of n copies of the system. So this is why it's called replica trick. You create n replicas of this. So you have to compute the partition function of n replicas of this system with the same disorder, average that, and then take this limit. Yeah, I'm correct. It's correct. You are swapping lots of. You're also swapping the thermodynamic limit with this limit, and there's lots of things that are problematic.
N of these has to be integer.
Yes. However, as I will tell you in 10 minutes, everything is exact in the end. Everything is correct. There's a proof.
But why do you have to identify n with the number of replicas?
Sorry?
Why do you have to identify n?
No, but this is, well, if you have Zn, Z to the n, this is just, by definition, is the partition function of n copies of the system. All with the same disorder, all with the same realization of the Jijs.
Not mathematically identical.
No. This is a mathematical. So you say this can be written like this. So okay, so I want to average this object. So okay, let me average this object. Right?
The thing is, mathematically it is shaky because n is an integer.
Yeah, correct. Yeah.
Why do you have to interpret n?
Well, you don't, but well, okay. Well, we'll
give a interpretation to n.
Yeah, okay, but you will see it on the next slide. Okay, so okay, now, and then you do this. So you write down this object, right? And then you do the average over the Jijs, and then you get an object that looks like this. So you can write this like this, and this is an integral over in a space of matrices. So this is now an n by n matrix, QAB, and you have some kind of this can be written like n is the number of spins, and then you have some exponent here, which I've written down here, right? Which depends on this matrix Q. And at that point, you're sort of thinking about integers, right? You're thinking about an n by n matrix, little n by little n matrix. And this is what's called the overlap matrix. So it's the overlap between replica A and replica B. So it's sort of, if I have two copies of the system with the same Jij, how similar is the state of this spin here and here in the two replicas, right? This is what QAB tells me.
I think that it depends on I. Before you can
Yeah, because if you do this in the end, everything in this exponent becomes a sum over I, and you get identical. This is a mean field theory, right? Because everybody interacts with everybody, so you can. This is how this n emerges, because well, the one would have to go into the details of the thing, right? But this is always like that you trade the site indices for, in this case, replica indices. Yeah, I did. Yes, well, I could have removed it. I could have removed it, but. So, and then, okay, so this is basically what Sherrington and Kirkpatrick did in their paper. And then you say, well, okay, now I have to proceed here somehow, right? So you have this space of n by n overlap matrices, and they are symmetric, and so you have n times n minus 1 over 2 dimensions, or entries in this matrix, independent entries. And now, this is from one of Paris's papers, right? The space of 0 times 0 matrices is very large, infinite dimensional, and we do not know how to write a generic matrix in this space. Right? Because you have to do this. It is an n by n matrix, and then you have to send n to 0, right? And you have n times n minus 1 components, and you have to send n to 0. In fact, for n to 0, the dimension of this becomes negative, right? So there's some kind of problems, right? Well, yes, but okay, when n, yes, okay, yes, sorry, so I should have written when n is less than 1. Yes, you're right. When n is less than 1, this is negative, right? Yeah, you're right. So you somehow go, okay, you have everybody, we live in a 3-dimensional world. Then at some point, people invented 4 dimensions, right? And you have these pictures. Then at some point, people invented the infinite dimensional spaces, like Hilbert space, right? Then people came up with non-integer dimensions. And now all of a sudden we're talking about negative dimensions, right? Now, so S and K sort of then said, okay, now I have to make an ansatz for this matrix. I have to use something. And you have these replicas. And the natural assumption is that there's none of these replicas is different from any other, right? Somehow, statistically. So you would assume that, okay, all off-diagonal elements in this matrix are the same. I mean, what replica 1 and 17 do should be the same as what 3 and 37 do, right? Naively. So this is what they wrote down, and then you can argue whether that. So basically, on the diagonal, don't worry about the diagonal. The diagonal doesn't enter in this calculation really. So they did this, and Q is what is this Edwards-Anderson parameter, and so then you have 2 order parameters: magnetization and this Edwards-Anderson parameter, and then you can distinguish depending on the solution where you have a paramagnet or a ferromagnet or a spin glass. In spin glass behavior, you see it when Q is non-zero, when there's a solution with non-zero Q. And this is sort of what they found, right? So they have this is the phase diagram from their paper. And somehow these phases are found in certain materials. So this is, right? So the paper by Sherrington and Kirkpatrick is called, I think, a solvable model of a spin glass. And well, this is their solution. So now, there's several problems then, which they noticed. So A, when you compute the entropy of this thing and you go to 0 temperature, you get a negative entropy. So which can't be right? Because it's a discrete system. The number of states. So you get minus Boltzmann constant over 2 pi. So this cannot be. So when they say this incorrect result is the most obvious indication that the procedure used above is not correct in all details. B, then this is sort of, it doesn't agree with simulations at low temperature. So this is the energy, and this is the entropy, right? So the solution predicts a negative entropy, and of course in simulations you get a 0 entropy here, or something close to 0, and the energy also deviates here. So these are simulations from 78. And you have to, this is a long time ago doing these simulations at that time. I think it's with 500 spins or something, right? So this is not And this is for those this is quite an achievement, right? In 1978, I would say. And then there is the Almeida and Thouless showed that this solution is actually unstable against fluctuation. So you have, I showed you this saddle point problem, right? And you have to find the minimum of the saddle point problem. And then you have to look, okay, you found an extremum, but is this actually a minimum or a maximum? And what A and T showed, Almeida and Thouless, is that this replica symmetric solution is not actually a minimum at low temperatures of this problem, of this saddle point problem. You extremize this object, but how do you know whether you have a minimum or a maximum? Right? So you have to look at the Hessian and the eigenvalues and so on. And this is what they did. So negative entropy, unstable at low temperature, and it doesn't agree with simulations at low temperature. So what now? So I went to the stairs and copied this. This is so. And then you need Giorgio, right? So he then found the solution, and I'm going to tell you what it is. So he said basically, it is not evident how to parameterize a matrix in a zero-dimensional space. Lacking better information, we can only proceed by trial and error. And then now he made an ansatz, which I will tell you about in a second. The only possible justification for the ansatz is the ability to reproduce the results of computer simulations. So he had no, right? So by some kind of intuition, he found the right way to proceed. So what he did is, okay, so I showed you this matrix where you have everything Q here and everything Q here. And he said, okay, well, let's divide this into blocks. Okay, so I have here a green block where I put a Q0, and here I put Q0, and then I have this block where I put Q1s. So you break the replica symmetry. So these ones, so the overlap between replicas within this group is Q1, but if you have this group with this group, it's Q0. So you're breaking the symmetry between the replicas. So this is called replica symmetry breaking. And then, so this would be one-step replica symmetry breaking. And these people sort of had tried, and this improves the thing, but for example, doesn't solve this entropy problem. And they said, wow, let's continue. Let's divide these blocks into another sub-block, right? And then so on. And then you say, this block, you divide it again into a block, into sub-blocks, and so on, right? So that's the idea. And this is very easy to visualize if you think of these as integers, right? So these are now 8 copies, and I've made a 2 blocks of 4, and then 2 blocks of 2, and so on. But ultimately, you have the n goes to 0, right? The number of rows and columns goes to 0. So this is a very weird space that you're operating in. So and so on. So one-step replica symmetry breaking, 2-step, and then infinite, right? And then ultimately, this Q, this parameter Q, you introduce a sort of continuous coordinate. So you don't have a Q0, Q1, and Q2, but you have a Q of X, a continuous. So if you do this again and again and again, you sort of get a Q of X. So this is a cartoon that I found somewhere. And then he sort of wrote these papers. These are the first papers on this. So the order parameter for a spin glass, a function on the interval 0 to 1. So he introduced kind of Q of X. So it's sort of a continuous function. And then if you have replica symmetry, this is just flat. If you have here this line, this is sort of one-step replica symmetry breaking, where you have one value of Q here and then another one of here. Then you have this step here with 4 steps. There will be 4-step replica symmetry breaking. And then you have finally a continuous line, which would be infinite replica symmetry breaking. And then you have to sort of look for that. And then, okay, this is from some time later, mid-80s, where people sort of then also try to simulate this. And in fact, this is what you see in simulations of spin glasses.
Ideal was a constant punch?
A straight? I think it can be arbitrary. I think this is an illustration, I think. I think in the end it is not, I don't think it's straight. Or this depends on temperature and what kind of a magnetic field you have and so on, so various different details. And I'm not actually sure if the functional form of these things is. So in the early papers, they do sort of one-step replica symmetry breaking, 2-step replicas. No, I don't think it's a straight line. No. I don't think. Well, anyway. So And then people, so then you can ask, okay, what's the probability if I take two replicas that the overlap is this and that? And then you get a prediction from the Parisi theory somehow, or some estimate of that. This is this dashed line, this dotted line here. And then there are simulations here by Peter Young. And that, I mean, this is again sort of, this is a small number of spins. And again, this is 1983, but it sort of looks like it, right? And then here, this is a, sorry? I think so, yeah, with the same couplings, right? With the same realization of the couplings. But this is not so easy to do. I think so. The people in Rome, I think they built a special computer to do this, right? And this is from a more recent simulation where these are two replicas, and you can sort of see that there's kind of no structure in this, right? If you just take a snapshot, you don't see anything. Looks like zero magnetization. But if you compute the overlap of these two, sort of locally, then you can see structure all of a sudden, right? So while these look completely structureless, they have something in common, right? And then people looked further at this in the 80s. So Marc Mézard and other people. So then they said, okay, now, based on this overlap, I can define a distance between states, say, right? And then take three states, A, B, C, and you have three distances. And then they used Parisi's ansatz and computed what is the distribution if I have three pure states and I compute the three distances, what do I see? And what they find is that either you have the states such that they are mutually equidistant, so all three distances are the same, or two separations are equal and is larger than the third. So you can't have all combinations. And so basically, for normal distances, you have the triangle inequality, and they had something like this. So the DAB is less or equal to the maximum DBC, DAC. So it basically means you cannot put a point C here in between. So the structure of this space is such that you have this. And what they then realized is that this is what's called ultrametricity. So you have to think of these states as on a tree. So you have these three states, A, B, C, and you say the distance between these states is sort of how many levels do I have to go up in this tree until they meet? So in this case, the distance between A and B is 2, right? I have to go up 2 levels. And the distance between A and C is 1, 2, 3. And the distance between B and C is also 3. Right? So two of these distances, there's one distance which is the smallest, that's between A and B, but the two larger distances are equal. Right? So the two separations are equal and larger than the third. And then you can sort of identify this as this is in this Q of X, the distance between these things here at the bottom, these two, this is the maximum Q that you observe. And the distance between, let's say, this one and this one, you have to go all the way up, is a sort of, it's the minimum overlap that you can observe, right? So these have the smallest overlap. and these have sort of, well, the Q max, the largest overlap is between states like this, where you have to only go one level up. So this is an ultrametric space of states. And then this has also been confirmed in simulations and so, okay. And then the idea is sort of that as you lower temperature, these states sort of foliate. So as deeper and deeper you go in temperature, the more sub-branches appear here. So this energy landscape becomes more and more rugged, and there's more minima inside minima and so on, right? So, and this is organized in this way that you have this ultrametric structure. And this is ultimately what leads to all this behavior. Well, this is one of these cartoons, right? So you have one of these rugged landscapes. That leads to this aging behavior because you're hopping around in these kind of states.
Where did you leave A1 to Z? Which state?
No, well, okay, these are just states, right? So these are, I think, what is pure states. I'm just saying what the states are that can occur, right? In this. I'm not sure I understand the question.
Well,
Yes.
Beta, gamma,
Correct.
to go from 120.
Correct.
Eventually, you have to leave A1 to Z. Some step.
At the end. you calculate everything as if it is an integer, and then at the end you send n to 0, right? When nobody's looking. Okay, and then now this is one thing that I find very interesting that I heard of as a PhD student at some point. So imagine you have one of these systems, right? And you quench it to a temperature T1. So you start with a paramagnetic state somehow. And you then suddenly lower the temperature to something T1. And then you will see that the energy goes down, right, slowly, right? And then at some point, you say, before you do that, you say, okay, let me fix a temperature T2. Let me think of a temperature T2. And that temperature T2 goes with an energy E2. So this is step 0. Let me imagine a fixed temperature T2 and associated with it an energy E2 of the system, average energy. Now, so I write this down, what this energy is, right? Now I do the following. I take the system in a high temperature state and I lower it to T1. Then the energy will go down. And if I let it continue, it will go below E2 and keep going down, right? So, but at the moment where this curve hits E2, right, I switch the temperature to T2. So at that moment, I'm at temperature T2, and the system has energy E2. So you would expect the energy to be flat from that, right? But this is not what you see. You see a bump. You see something like this. So this is this Kovacs effect, right? So you see this bump, and I don't know, this is some memory effect that I think also depends on how exactly you do it and so on. These things equilibrate at different length scales and so on. So I don't know. I found when I first heard about this, I found this very interesting. This is from a simulation. What kind of system you do? I think so. Yeah, that's correct. That's correct. You're not in an correct. Well, yeah, okay, but anyway, there are all these things. There's aging. There's what they call rejuvenation. So you can make a sample younger again and so on. So anyway, so now you ask me all these maths questions. So there are these people. Francesco Guerra. So he was the first, so these are mathematicians, okay, or mathematical physicists. And there's this paper by him, or from him and Toninelli, 2002. So we present a simple strategy in order to show the existence and uniqueness of the thermodynamic limit for the SK model. So they showed that the thermodynamic limit exists about 27 years after, right? So right? So, okay, the thermodynamic limit exists. And then there's this paper, which is a year later, 2003 or something. Our main result is that the quenched average of the free energy is bounded from below by the value given in the Parisi ansatz. So the true energy, the mathematically rigorous energy is bounded from below by Parisi's result, right? So this is what they say. Uniformly in the size of the system, okay, whatever, right? So these are, so, and then Talagrand, I think in 2006, showed, it sort of proved the other bound, that the energy is also lower than the Parisi's formula. And then you have a bound from below and a bound from above, so it must be correct, right? So he completed the proof. So we compute the free energy of the SK model for spin glass at any temperature, confirming the celebrated prediction of Parisi. And this is mathematically rigorous. I don't think so, but he won. So he has this book. He won this Abel Prize, which is sort of, yeah. So I think last year. I think for the Fields medal you can't be above 40 or something, right? So probably, look, I don't know for sure, but looking at him, it seems. Yeah, but when you are awarded, well, okay, yes, yeah, but okay, I don't know. Anyway, so the answer is this is rigorously proven by now, right? Okay, and then there's also experiments where you see replica symmetry breaking in lasers and optical, I don't know, various nonlinear waves and so on, right? So actual experiments like laboratory. So I imagine for some people in the audience, this could be interesting to read about. I don't know. I mean, I don't know what these experiments are, right? Really in detail. Yeah, I think I don't know. To be honest, I don't know. I didn't look at these papers in detail. I don't know. Well, I assume. I don't know how they do it, right? How exactly do you create a replica? I don't know. Well, so anyway, I'm going to skip that. So well, I will. So then there's this question: what does this have to do with real glasses, right? There's structural glasses like them, and people look at these sort of things, and there's the glass transition and the glass problem. So basically, if you look at the viscosity of certain liquid materials, and then you lower temperature. So here, this is glass temperature over. So if you lower temperature for these materials, the viscosity shoots up, and then they have a definition and say when the viscosity is 10 to the 13 in some units, we say the glass transition has occurred. That basically means that the timescales, the relaxation timescales, are so long that you in experiments can't see them anymore. And then if you plot it like this, they distinguish between strong and fragile glasses and so on. And these are associated with what they call dynamical heterogeneity. So in simulations, you see regions which are very active and other regions which are not very active and so. And then there are these experiments like this one, the pitch drop experiment. So this is some substance that I don't know exact pitch. I don't know what exactly this is. This was started in 1927, right? In this arrangement. And you can see this drop form, right? And then every now and then a drop falls. Namely, in 1938, 1947, 1954, 62, 70, 77. So there have been 10 drops or something since 1927, right? So this is an extremely slow dynamics, right? Somehow. And I don't know. So if you're a PhD student and you're working on this, it could be that drop, right? You're doing your PhD, right? Anyway. Okay, so now in the last, I don't know, now we have to choose, I think, because so this is a sort of timeline. And then there's been lots of activity after that, of course, which I don't have time to talk about, and also I don't know enough about it to talk. And then there's structural glasses, and there's been various applications in neural networks, in optimization problems, in something called the minority. This is sort of when my PhD was on that. But that was a relatively short period and it stopped abruptly. At some point, nobody cares anymore. And then there's sort of complex ecosystems since, I don't know, the last 10 years or so. I don't have that much time. I'll probably talk about neural networks and the optimization problems. So neural networks. So, I mean, there are some people in the audience who know more about this than me. But the idea is that you have neurons and they communicate with each other. And then react to the inputs. And this is again from this picture is again from the Nobel Prize picture, from Hopfield's Nobel Prize. So you think of the Hopfield network as a system here of neurons, okay, in this case, and they are coupled with couplings Jij, and each neuron can be in two states, -1 or 1, firing or not firing, if you like. And then each neuron at the next step sort of collects the inputs from the neurons it is connected to, and then decides whether it wants to be up or down in the next step. And these Jij then you have to ask, what are these Jij? How should they be? How should I model this? What should I do with this, right? So this is the generic idea. You find this kind of thing in Hopfield's paper, 1982. And then now imagine, so you have neurons, so I don't know how many these are, right? The dots here, and you want to store a pattern, say this letter J here, right? So you want some of these to be up and some of these to be down. So you have n neurons, I don't know how, this is maybe 15 times 20, or I don't know what this is, right? And each of them you want to store a pattern, so you have Xi1 to Xin. This is the desired state that you want to retrieve. Each of them is -1, 1. And then you have the actual state of the neurons and the SI, and then you compute an overlap. So this sort of basically counts how often does the state of the system agree with the pattern. So for example, this could be, if I have only 8 nodes, I could have this pattern, right? And then here, if the state of the system is like this, if I did it correctly, half of them agree and half of them don't agree, so there's basically no overlap. And here, you have a good overlap, right? Because this one agrees, this one agrees, this one agrees, this one agrees, this, I don't know, I think I did one that didn't agree, right? Well, maybe I don't know, maybe it's perfect overlap, I don't know. So, okay, you can say, well, the Hamiltonian, I say, is minus the overlap squared. the higher the overlap, the lower the energy. And so I'm talking about retrieval here now, right? I'm not talking about the training the network or anything. I'm trying to saying, okay, I want to retrieve this pattern. I want to give this thing some kind of input state, and then it should, following the dynamics, should retrieve this desired pattern. And so here, then you can have 10 patterns, if you like, right, Liz? Right? Or how many of these are? 10. And so you maybe have this one and this one and this one, and then some kind of state of the network. And then you want it to somehow converge to something that it is at least one of those patterns, right? And then depending on where you start, you may go to this one or this one or this one or this one, right? It's a sort of, and then you say, well, the Hamiltonian is then kind of the sum of these overlaps. I have different patterns, mu, that I label with mu from 1 to p, and so this is sort of the idea, right? I drop the thing, the ball somewhere here, and then depending on where I start and the dynamics, I end up in one of these patterns or close to one of these patterns. This is sort of the idea. And here's a simulation of this. This is from Ton Coulin's notes, right? So you start with this configuration, then you evolve this, and one of the overlaps sort of becomes positive, and the other ones are basically 0, and then you retrieve this pattern here, this one, in this case. And if you had picked a different initial condition, you would maybe have converged to a different one. So, and this thing with this overlap can be written in this form, where the Jij are like this. So this is called pattern disorder, right? So you have these patterns that you want to store, and then you can write this Hamiltonian in this way. And then if you now assume that patterns are chosen randomly from the space of all patterns that are there, then you have a sort of disordered problem. And then you say, well, what's the ground state of this thing? How many patterns can I retrieve? And so on. And then this is what these people did in 1985. So they computed the phase diagram of this thing. And there's a spin glass phase, a paramagnetic phase, and then some ferromagnetic phase, and a mixed phase. And retrieval basically works here. So now you can say, well, even at 0 temperature, so when there's no noise in the system, the retrieval only works up to a certain ratio, alpha, of number of patterns divided by number of neurons. So if you have a given number of neurons in the system, you can't store more than 0.14 or whatever that is, times that number of patterns. If you have 1,000 neurons, you can't store more than 148 patterns in this thing, or retrieve for random patterns. Yeah, okay, yeah, well, okay, yes, but generically, yes. I think it's large. Okay, so there are other ways of calculating things. So, for example, this. Okay, so this is. So, who of you have heard about Elizabeth Gardner? So this is really where in Edinburgh. Wow. So, oh wow. So you used to tell me. So she was exposed to these kind of problems, and then asked sort of this question the other way around and said, given the patterns, what Jij's, what is in the space of all Jij's, what is the volume of Jij's that allow me to store these patterns? This is now called a Gardner calculation. And so she, I don't know, was apparently exposed to these kind of problems, and within a few days found the solution to these things, right? So that's a remarkable achievement, and so this is her. And then if you want to read something interesting, read this. So she died at the age of 30 of cancer, and was working with Derrida. And so there's this paper. There are 3 unfinished works on the optimal storage capacity of neural networks, and this is the conclusions of this paper. And it says Derrida alone. She wasn't there anymore. So it is with a great deal of pain and emotion that I come to the end of this paper. So it is hard to accept that our collaboration, which I found enjoyable and stimulating, should have ended prematurely. This work is unfinished. What is written here corresponds to what was discussed with Elizabeth between January 87 and May 88. And we started working on models A and C and so on. Both of us were visiting Hebrew University in the spring of 1988. She died in June 88. So this is it's truly remarkable. And this thing, and then there's also Martin Evans has written about this, also turning statistical mechanics on its head, right? Because she, instead of looking at the state of the space of states, looked at the space of couplings. So if I want a certain state as a ground state, what couplings allow me to do that? So this I will skip because I don't have time. I want to briefly to talk about combinatorial optimization because it's maybe something that you have not heard about, or I'm not sure anyway. So take the problem of graph partitioning. So you have a network like this, and you want to divide it into two equal parts. See? But you want to minimize the number of links between the two parts. So, for example, you have a certain number of components in a computer that you have to put somewhere on two chips or something, and they have to communicate with each other, but you want to minimize the number of kind of wires or communication lines between the two components, right? So, for example, you can do it like this here, right? So these four nodes are these four. I have preserved the network, right? So the topology of the network is the same. So these four are these four, and these four are these four. So here I've done it with 3 links in between. So here it's relatively easy, I think. I'm not, probably this is the optimal solution, I'm not sure, but I guess. But you can easily imagine if you have a lot of links, then it's, and a lot of nodes, it's not so easy anymore, right? And then there's 2 to the n combinations, or 2 to the n now, but if you make equal components, well, I don't know. No, it's not 2 to the n, but a large number. So, and then you can write down, if you have the adjacency matrix, you can write down the Hamiltonian like this, right? You say, to each node, I have to say, should it be left or right, plus or minus 1, and you write the Hamiltonian like this, and now you find the ground state. Or this is the knapsack problem. So the backpack problem. So you have a backpack, you go somewhere, and you can only put 15 kilograms into this thing. And now you have objects that you can put in, and they each have a weight and a value. And now the question is, okay, take the largest value with you, right? But you can only put 15 kilos in there. So what should you take, right? Which ones should you put in the bag to maximize the monetary value, but not exceed 15 kilos? And these are sort of optimization problems. Okay, this is with the weights and the dollars, but you can sort of imagine in traffic systems or in any sorts of optimization problems in industry that this kind of thing can occur, right? So this is a combinatorial optimization problem, or this the traveling salesman problem that you've probably heard about. So you're a salesman or a saleswoman, and you want to visit certain locations, and you want to have the shortest trip as possible, right? You want to go to each of these locations, and you want to minimize the distance that you travel. What sequence should you do? So, for example, these are your locations. What do you do? What's the shortest trip that you can do to connect all these, right? It's apparently like this. Or here now, this is the vertex cover problem. This is the museum, okay? And these are rooms. The nodes are rooms, and there are corridors, and there are pictures hung in the corridors. Now you have to put guards, right? And if you put a guard here, they can watch this whole corridor and this whole corridor, right? See, and now you want to put the minimum number of guards here so that every corridor is watched. So, for example, this is not a solution, right? You can put a person here, they can watch this and this, but this is not guarded, right? So you have to put a second person here, right? And then you've solved it. So this means you want to cover the vertices, and for each edge, at least one of the neighboring vertices has to be covered. So there's a vertex cover problem. And there's also other related problems like vertex coloring, where you color the vertices and no pair of neighboring color and so on. And then there's satisfiability problems, KSAT. So imagine you have n binary variables, and I 0, 1, and now you have clauses. So you have the clause is x1 or x2 or x6. Now you want to assign kind of true or false, 0 or 1 to each of these, so that this clause is fulfilled. So this means that either x1 or at least one of these 3 has to be true. And so this means x1 has to be true, or x2 has to be true, or x6 has to be true. So at least one of those 3 must be in state 1. And then you have another clause, maybe this one, x7 or x17 or not x20. So you have either this one must be in state true, or this one must be in state true, or this one must be in state false. Then this thing is fulfilled. And then you have a long list of these, and you want to fulfill them all. Right? And of course, at some point, variables will appear in multiple clauses. Like the x1 appears here, here, and here. And then you say, well, I have n of these variables and alpha n clauses. And clearly, the more clauses I have, the more difficult it will be to fulfill them all. And at some point, it becomes impossible. How many can I do, right? And then people looked at this. They look at this, and these are these combinatorial optimization problems. So this is a paper in Science from 2002, where they computed sort of the complexity of the space of solutions. How many possibilities are there, and so on. And there's basically a cutoff above a critical value of this ratio, number of clauses divided by number of variables. You can't do it anymore. And then they invent these message passing algorithms where you can actually solve instances. And then people look at sort of the landscape, the energy landscape of this, and the geometric structure of the set of ground states. You find at low alpha, low number of clauses, basically everything is a solution. Then this sort of fragments into a number of clusters. Then all of a sudden you have exponentially many clusters, and then it's dominated by a small number of clusters again, and then you have no solutions. And so people have studied this, and this is obviously machine learning problems, sort of relevance, what this landscape is. And this is all on based on methods that originally came from spin glass physics. So, okay, so I'm not going to talk about this because you know this already, or I'll talk about it some other time. So if you want to read about this, there's this book from 1987, it's very old, but very, very good. Then there's a new version. So this is spin glass theory and beyond, and then there's spin glass theory and far beyond. But this is from 2 years ago. So I have not actually seen this book. But it has a lot of chapters on a lot of different applications: aging, glass forming, the Gardner glass, polymers, KPZ, random lasers, message passing, quantum glasses, neural networks, biological molecules, ecosystems, whatever you want, random satisfaction problems. You can look there. And then, well, and then there's a book, it's also old, I know, probably 20 years old or 25, by Fischer and Hertz about spin glasses. And then there's these reviews by Andrea Cavagna and co-worker, Spin Glass Theory for Pedestrians. And then, so David and Scott Kirkpatrick, they wrote this thing that appeared kind of 2 weeks ago. This is very nice to read. And then there's also some kind of these kind of things. This is David's lecture notes from 98. So, and with that, I've reached the end of what I wanted to say.
Well, thank you very much. Very nice talk. There were already quite a lot of questions, but there is time for 1 or 2 more if you want. Yeah, great. Thank you, Raul.
You mentioned at the beginning there were 2 key aspects of the experiments and the system was positive and negative interactions and randomness. I mean, you have a small number of iron atoms in the background. What happened with the randomness?
Because they are in random positions.
Yeah, but what happened to the random? Okay.
So the idea is that you have these impurities there, and then these 2 impurities interact, or any pair interact.
Yes.
And now this could be a ferromagnetic interaction or an antiferromagnetic interaction.
Okay.
And this depends on distance via this.
Okay,
right?
So your system is only the system of
these
iron
impurities.
atoms
Correct.
put on a lattice.
Correct.
So when people do 2-dimensional lattice and so on, this is...
Yeah, so initially you have the thing, okay, you have these impurities thrown in, the distances are random, and that determines whether the interactions are positive or negative, right? The distance between any 2.
Okay.
And then you say, well, now I want to make a model of this that I can treat. So I say, okay, I only look at these impurities, I put them on the lattice, but I choose the couplings random. Yeah, I should have explained this.
Thanks for the talk. Maybe I lost or not, I don't know. There's a physical reason for the RSB trick, or they didn't?
Well, there is all this thing that comes afterwards, right? And then they understood ultrametricity and how this relates to aging and the dynamics and so on. There's a lot more about the dynamics that I haven't said, but I'm not sure you could tell sort of before the Parisi solution that this must be so based on physics, right?
Yeah, that's what he said, basically.
I think he just said, as he said, we have to proceed by trial and error, and I tried this, and he seems to agree with simulations, right?
I meant a posteriori.
Then I think afterwards you sort of, it has to do with this organization of the states and so on, right? But
okay, thanks.
Well, that's all. Thanks a lot.
All right.
Thank you for coming.